Zener diodes. In this presentation, we're going to be looking at what makes up a Zener diode, how does it function, what are some calculations to do with the properties in the circuit, and then we'll take a look at some ratings. Like most electronic components, Zener diodes are manufactured from silicon carbide. The layering and use of P and N-type material, or silicone, is similar to a standard diode. Here's a comparison between the two. Standard diode on the left, Zener diode on the right. On the left, a standard diode has a single PN junction. P and N-type material is used. Same on a Zener diode. We have P-type material and N-type material, but you can see the proportions of them are much different. A Zener diode still has an anode and a cathode connection. A Zener diode shares many of the same characteristics of a standard diode. It has a PN junction and is polarity sensitive. The main differences of a Zener diode are, one, it's designed to be connected reverse bias, so a little bit different. It's normally going to conduct current in the reverse bias direction without damage. It's used to maintain the voltage across a load, and sometimes that's referred to as a regulator circuit. And it's connected in parallel with loads because it's meant to regulate the voltage across a load. You'll notice a Zener diode, the schematic symbol, has these 245-degree lines that come off it, and that means that it can actually conduct current in both directions. What I mean by that, it's normally used in a reverse bias connection, and current will only flow through it at a certain point. If you put it forward biased, the Zener diode would act as a normal diode. However, that is very rare to see in practical application. Well, let's see how a Zener diode will function in a particular application. So Zener diodes are used to maintain a constant voltage across a load. The voltage a Zener diode maintains is called its Zener voltage rating. So we can see here, we've got a Zener voltage rating of 10 volts DC, and it's got a wattage rating. When the source voltage connected to the Zener diode exceeds the Zener voltage rating, current will flow through the Zener. A resistor is always necessary to limit the current through the Zener. So there's my series connective resistor. When current flows through the Zener, a constant voltage will then be present across it. The constant Zener voltage will be maintained regardless of the magnitude of current that flows through it. So that's sometimes referred to as a dynamic resistance device because the resistance of it will change dependent on the voltage that is present across it. So kind of an interesting application. Well, let's see a situation where we've got a Zener voltage regulator circuit and the source voltage increases. Notice there's a voltage across the Zener, and that voltage across the Zener is a constant value, and the load is going to have that voltage as well because it's in parallel with the Zener. Let's say the source voltage increased. Notice as the source voltage increases, the currents in various locations increase also, and that's due to the voltage across this resistor that's series connected. So the current increases here, and the current increases through this Zener diode. But notice, the voltage across the load remained unchanged, and that's the entire purpose of this system. Well, let's take a look at a different scenario. What if we had a variable load, but the voltage of the source remained constant? As the load ohms goes down, notice the current flow changes. Okay, so the current flow to the load goes up, and that's by virtue of Ohm's law. If the ohms goes down, the current goes up. And this is due to the voltage remaining constant. The voltage did not change. And so the ohms of the load here did not have any effect on the voltage across the system. So the current through the load increases, the current through the Zener increased, however the voltage across the load remained unchanged. Well, to prove how all of these things occur and why they occur, we're going to do a few calculations, starting with calculating the voltage across a series resistor. Now, the Zener diode and the resistor create a basic series circuit. You can see here, series circuit. If the Zener is conducting and maintaining its Zener voltage, the resistor voltage drop can be calculated simply by using Kirchhoff's voltage law for the highest expected source voltage. So let's say we expect the highest source voltage to be 20 volts. Then what we're going to do is take that 20 volts, subtract the Zener rated voltage, and that should give me the voltage across the resistor, and that would be 10 volts. So there we have 10 volts. Now notice I've also got 10 volts listed here across my Zener diode. Now, the second calculation would be calculating the resistance of the series resistor. The Zener diode and the resistor, again, create a basic series circuit. That means the resistor is sized to restrict the current flowing through the Zener diode so it does not exceed its rated value. Now, we don't have a current value for our Zener diode. So what we're going to have to do here is determine the current based on the wattage and the voltage of the Zener diode. So the max Zener amperage is equal to the power divided by the voltage. And that would give me on this particular Zener 5 amps max. So what we're going to do is we're going to take that series resistor ohmic value and calculate it from the voltage of the resistor that's present across the resistor and the current that the Zener diode, the maximum current it is permitted to have flow through it. If we exceed this value, we will damage the Zener. So 10 volts divided by 5 amps gives me 2 ohms. So that's a 2 ohm resistor that I would have to connect in series with the Zener diode. Third calculation, let's calculate the values with a load connected to the Zener. And so you can see here there's a number of question marks, but a whole bunch of numbers are still the same. And that's because, well, my Zener diode here, that is going to have 10 volts across it. And here we've got 10 volts across the resistor. It's a 2 ohm resistor. Let's see what else we have to calculate. So with a load connected, the total current through the Zener will change. The voltage across the Zener and the voltage across the resistor will not change. Using Kirchhoff's current law, we can then determine the Zener current. So if we look at this top arrow here, this is simply 10 volts divided by 2 ohms, and that gives me 5 amps. Great, so that's 5 amps flowing there. Now what about over here? This arrow, this is the ohmic value and the voltage across the load. So 30 ohm load, 10 volts, that's 10 divided by 30, that gives me 0.33 amps. Now to determine how much current my Zener will now carry, it's not 5 amps, it's going to be Kirchhoff's current law. And Kirchhoff's current law says 5 amps minus 333 milliamps. That would give me 4.667 amps. The impedance of a Zener changes as the load or source fluctuates. This change in impedance, also known as the dynamic resistance, is what allows the Zener to maintain its rated voltage. So let's adjust the source voltage to the Zener circuit down from 20 volts. Now what properties will not change? Well, the voltage across the Zener won't change, the voltage across the load won't change, and that means the current through the load won't change. So let's drop it down to 18 volts. Let's calculate the mystery values that we have listed on the diagram. We're going to calculate the voltage across the resistor first. And remember, it is simply a series loop. The series loop is right in here. I already know what the voltage drop is across the Zener diode, so that's 18 minus 10. So 18 minus 10 is 8 volts. Now what about the current through the resistor? Well, that's just Ohm's law. I now have 8 volts and 2 ohms. So 8 divided by 2, that should give me 4 amps. And then we can see here, there's the 4 amps flowing. Now Kirchhoff's current law. How much current's flowing through the Zener? 4 minus 333 milliamps, that gives me 3.667 amps. Well, instead, let's adjust the load ohms in the Zener circuit. Well, in this situation, again, we need to know the properties that will not change. The voltage across the Zener won't change. The voltage across the load won't change. The voltage across the resistor then won't change. And the current through the resistor won't change. So that means all we're going to do is we're going to calculate the current through the load and calculate the current through the Zener. And that's where those two question marks are. So we're going to go from 40, and now we've got 250 milliamps. And that's from 10 divided by 40 instead of 10 divided by 30, if you remember from the last example. And for the current flowing through the Zener, that is Kirchhoff's current law again. 4 amps minus 250 milliamps gives me 3.75 amps. Again, the impedance of a Zener changes as the load or source fluctuates. This change in impedance, also known as the dynamic resistance, is what allowed the Zener to maintain its rated voltage. Now, just like a standard diode, Zener diode characteristics are often represented with an IV curve diagram. So here we can see It shows that it would act like a standard type of diode if you reach the forward bias or forward voltage in a forward bias connection. Now, normally, Zener diodes are not used for this application, but it's interesting to know that they could be. If we go back in the reverse bias calculation, we had a reverse leakage current that could occur up into Zener voltage being triggered, and at the Zener voltage being triggered, the current value increases. Eventually, if I were to exceed the peak inverse voltage value, this here would cause destruction of the Zener diode in much the same way that a standard diode would. So remember, the Zener breakdown voltage, that is what allows the current to flow in reverse bias through a Zener diode, and this value of current here will change based on the characteristics of the circuit. The Zener diodes are not typically designed to carry humongous load currents, and due to this, they're typically smaller in size than what you would expect from a standard diode. So we can see here Zener diode, the glass sort of one. This one looks like it's connected to a circuit board. That's a stud mount. There, for comparison, I mean, that's a pretty small Zener diode compared to a diode on the left. And if we compare it against a pencil, I mean, that is significantly different. So all Zener diodes will come with ratings from the manufacturer, and this will provide detail on the maximum current, power, Zener voltage, and inverse voltage, and temperature. So, a summary of Zener diodes. When connected in reverse bias, the Zener voltage rating is exceeded, the device will conduct current. Current through the Zener diode will vary depending on the source or load. The polarity of source across the Zener diode must have positive on cathode, connected in parallel with loads or devices and used to regulate voltage across loads.